Hello, today we're going to show you how to perform a conventional PCR. I'm here with my friend Andrea. Please introduce yourself.
Hi, my name is Andrea and I'm a neuroscience PhD student and a friend of Bruno's.
Great. So we're going to perform a PCR today, right? What is the goal? Why are we doing this PCR?
Well, the goal of doing this PCR is I have these mice that I want to see if they inherited a transgene that I'm interested in, and so we're going to run this PCR and find out.
So the mice has this Cre transgene, and you want to make sure if they have or not.
Exactly.
Okay. So how are we going to do this? What are the steps that we need to do?
So the first thing is we need to digest the tails that I obtained from the mice. Then we're going to do the PCR and then run a gel electrophoresis.
Okay. So let's do it. You can do whatever you need to do. We're gonna make sure that we get in the camera all the little details, the vortexing, all the little details. So if someone is watching the video, they'll be able to do it in their own lab just by watching this video.
Okay, sounds good.
Let's do it. So we had to take a little piece of the mouse. Sorry about that, but we had to take a little piece of the mouse tail. So we're gonna digest that tail to make sure we get the DNA that's in that tail so we can use in our PCR, right?
That is correct. So what I'm using here right now is this alkaline lysis buffer, which has sodium hydroxide. We're gonna put these tails on the heating block for 30 minutes at 95 degrees Celsius. And then we're gonna take them off the heating block and add tris to stop the digest.
Sounds good. And then we should be done with the digesting, right?
That's correct. So now I'm just moving these tubes to the heating block and we'll wait 30 minutes. Now that we have the samples off the heating block, I'm gonna add some of the neutralizing solution, which has tris, and that will stop the digest.
Sounds good. So do you shake the solution?
Yeah, so I usually just shake it a little bit, and then once I add it to the tube, I like to pipette up and down.
Also, you
times.
usually just flick a little bit with your finger.
That's correct. Yeah,
Okay.
I don't like vortexing it.
Okay.
Okay.
So now we have the DNA, right?
Yes. So now we have our DNA, so we can proceed to the PCR, like gathering all the reagents and running the PCR.
Okay, so let's go to the PCR. So I'm seeing here what you use for a PCR. So you use this Taq polymerase mix, right?
That's correct.
So I'm going to assume that it has the NTPs, the magnesium. So instead of adding all of them separately, you add the Taq polymerase, the NTP, and the magnesium, everything, but it's already in a mix.
Yes, that's correct.
That's what most of people use, actually. Okay, so after that, you use this Cora load concentrate. So what is that?
So basically what the core load is, it's a loading dye buffer. So at the end, instead of having to add the loading dye when you're pipetting the reaction into the wells, you can just already have it ready to go.
Okay. So other than that, you're using the primers, right?
That's
so
correct.
People watching this video, they probably watch our first video that we explain what are primers and they target specific regions of the DNA. So what regions are you targeting with this primer?
So here we're going to be looking for the expression of Cre, so whether a mouse has Cre or not.
Okay, so is the transgene that we're looking for, right?
Yeah, that's correct.
So the mice that has the Cre transgene, the primer is going to be able to bind, and the PCR is going to happen, the amplification is going to happen. The mice that does not have the Cre transgene, the primer is not going to bind, and nothing's going to happen.
Yeah, that's correct. We won't see a band for that.
Sounds good. So let's do it. I see you have this minus and plus tubes. What is that?
So it's good practice to run your samples with some known samples. So what I have here is a negative control. So this is DNA from a mouse that I know doesn't have Cre. It doesn't have the Cre transgene. And then my positive control is from DNA from a mouse that I know has Cre. And then it's also good to have a water control to make sure that there aren't any contaminants in your buffers and your water. So I'm just gonna grab an Eppendorf where I'll be doing my master mix.
We're gonna make sure to share this calculations with everyone in the screen. But Andrea is doing the master mix, good for 8 samples. She actually has only 7 samples that are the 4 mice that you want to check, the negative control, the positive control, and the water control. So it's only 7 tubes, but she makes a master mix for 8, so we have extra room. Correct?
That's correct. So I just added the TAC Polymerase master mix, and now I'm adding the water. And then next I'll add the coral load. And it's a good idea to keep all of these reagents on ice. That's why we have the little ice bucket here. Alright, so now I'm going to be adding the primers. Alright, so we're all set. So now that we have the master mix, we can grab the PCR tube strip. So I'll bring this over here.
So you have this master mix that is good for 8 samples.
That's correct.
So we have everything here besides the DNA, correct?
Yes. Mm-hmm.
So the DNA are in separate tubes. We're just gonna put the master mix plus DNA in each of these tubes, correct?
Correct. So the first thing is I'll put the master mix in all the tubes, and then I'll go in and add the DNA at the end.
Sounds good.
So for this PCR, we calculate it to have 19 microliters of the master mix.
And you keep the same tip, right?
Correct. So since there's nothing in these tubes already, so we can actually just use the same tip. And it's okay to touch the wall of the tubes. Now we're going to add the DNA sample. So we'll add 1 microliter.
So now because you have different samples, you want to make sure you change the tip so you don't cross-contaminate, right?
Correct. All of our DNA samples into the tubes. We can add the cap, and then we'll spin this down and then put it into the machine.
So this tube is supposed to have everything, right? Has the DNA sample, the TAC polymerase mix, the primers, and the coral load concentrate, right?
Yep.
Okay, so there's the thermocycler, right?
That's correct.
Okay.
So here we have the protocol that we're going to be using for this PCR, and I'm just going to hit run and start.
We're gonna make sure to put all the temperatures for all the cycles that Andrea used in this PCR. this works for Andrea. I want to make sure that we show exactly the way that she do. You might have to change the temperature depending on which primer you have. Things might vary, especially the handling temperature. So you got to figure out by yourself, but we're going to show you exactly the way that works for Andrea.
That's correct. And then the number of cycles that you may be using for your PCR may vary as well.
Sounds good. Let's wait. Now we perform PCR. So how do we know if the PCR worked, right? Because we're going to take it out from the thermocycler and it's just going to look like a liquid. Like, how do you know that the reaction actually worked? So to check if the PCR worked, we're going to do gel electrophoresis. That is this technique that we're going to separate the DNA fragments according to their size. So we're going to have our DNA. We're going to mix it with ethidium bromide. That is this dye that's going to bind to DNA, and it's going to glow as you expose it to UV light. Something that we're going to do really quick. So we're going to put this DNA plus ethidium bromide in a gel. This gel is made of this sugar called agarose, that if you can zoom in the molecular structure of this gel, you see there's a lot of pores, like a little matrix. So as we make our DNA travel through this gel, the big chunks of DNA, they're going to have a hard time traveling through the pores. So they're going to be stuck and they're going to move slow. The little chunks of DNA, they're just going to pass through the pores and going to make it faster. So as our DNA travel through the gel, we are supposed to separate the big chunks from the small chunks. The question is how we're going to make them travel. We're going to use electricity, right? So we're going to use this chamber that conducts current, has electricity passing through it. So it has a positive pole and a negative pole. One thing you should know is the DNA has negative charge. So as we put the DNA in the negative side of the chamber and we turn on the chamber, we're going to see the DNA being attracted to its opposite charge, that is the positive. So using electricity, we make the DNA travel to the agarose gel. And as I said before, the big chunks are going to take longer and the small chunks are going to go faster. So we're going to have our DNA fragments in form of bands in an agarose gel. And we're going to show to you right now. Right?
Yeah, that's right.
Let's do it. So we're going to do the agarose gel now, right?
Yeah.
So please tell us how to do it.
Okay, so what we're going to do is we're going to add the agarose into the beaker, then we're going to add the TAE buffer into the beaker, and using a paper towel, I'm going to create like a plug onto the beaker so that none of the agarose spills over when it's in the microwave.
That's good.
Okay, so
what are we doing after we microwave it?
So after we microwave it, we're going to let it cool for a couple of minutes.
Okay.
And then we'll add the ethidium bromide and then we'll pour out the gel. All right, now that the time's up, we can take it out. All right, so you just want to make sure that all of the agarose has really dissolved into the TAE buffer. Make sure that there's no like grains still in there. And then you allow the cooling process to take between 2 to 3 minutes. Some people like to speed it up by running it under cold water. All right, now that we've waited a couple of minutes, I'm just touching it and it's not too hot to touch, so I know it's ready. And you kind of want to work quickly because you don't want the gel to like polymerize or solidify too early before you add the ethidium bromide. So what I'm going to do is I'm going to add the ethidium bromide into the beaker, and then I'm going to pour that mixture into this chamber. So this is the chamber, and here is where we'll be adding like the mixture, and that's where the gel will be formed. Then we'll add some combs, and we'll wait a couple of minutes until it's polymerized.
So I don't know if you guys realize, but Andrea wasn't talking while she was on the top of the gel, and I don't know if you realize, but she discarded the ethylene bromide tip in a specific disposal. So ethylene bromide is this compound that it's very toxic. You definitely don't want to be like breathing, especially in the warm, in the hot gel. You don't want to be like sniffing. You don't want to be exposed to it, right?
Yeah, and that's why we wait for the gel, like the agarose, to be cool, because you don't want it to be boiling and then you add the ethylene bromide and then you're breathing in the fumes. So be very cautious. All right, so now that our gel has polymerized and you can see that's a little bit more opaque, we can proceed to the next steps. So we'll remove the combs, we'll adjust the gel so that the well is located near the negative pole so that the DNA can travel to the positive pole. We'll add more of the TAE buffer to fill the chamber all the way up to the fill line, and then we'll add our loading samples.
So one thing you got to notice is, more than adding the samples, Andrea is going to add the DNA ladder in the first well. So this DNA ladder is this compound that's going to give us different bands, and each of these bands are expected to have a known base pair size. So let's say that your amplicon from your PCR, it's supposed to have 100 base pair size. You would expect that band should be at the same alignment, the same height of the DNA ladder 100 base pair size band. So that's how you figure out the size of your amplicons. We're going to show you in the Rio gel in a couple of minutes. Let's do it.
Okay. I'll remove the combs. You have to be careful because you don't really want to slice any of the wells, especially if you have the exact amount of wells that you need for your samples. And then something that I do to kind of help bring some contrast to when I'm loading is I use the comb and I put it on the bottom. So I also need to add the TAE buffer. I'll just pour it in. And I filled it in all the way to the fill line.
So you put the comb in the bottom so you see more easily the samples falling in the well, right?
Exactly, because sometimes it can be a little bit difficult, especially if you have a white background. So I'll add 10 microliters of this ladder. It really depends on which ladder you get. I already got one that's already prepared with the loading dye, so I know how much exactly to add. You want to be careful not to puncture any of the wells. And I like to open each of the samples one by one so I remember which one I already took from. And I like to pipette up and down. So I ran out of wells on the top, so I'm just going to go to the bottom. You can choose to run another ladder here as well. For this purposes, I'm just going to have one ladder. All right, so now that I'm done adding everything, you want to get the cover for the chamber. And you want to make sure that it is positioned correctly. So the black is negative, the red is positively charged. So when I do this, I like to kind of always keep the chamber in the same way. So I always like to have all the plugs on the right so that I never really have to worry about the position of the lid. And make sure it's closed all the way. And for this gel electrophoresis, we're going to run it at a constant 100 volts. And then you want to click run, and you want to make sure you look for bubbles. So if you don't see bubbles, it means something's not working. It could be the buffer. It could be that you just didn't close the lid tightly. So always check for the bubbles before you abandon it for a couple of minutes, because you may find that you thought you started it and you came back and nothing ran. So always double check that.
And again, this works for Andrea. Is it gonna work for you, your specific gel and your specific samples? Maybe not. You figure out exactly the voltage and how long you're gonna run these gels.
That's right. So for this one, we're just gonna run it about 30 to 40 minutes. Usually then I'll check really quickly under UV light and then take an image. Okay, so now that we have finished doing the gel electrophoresis, we can transfer our gel onto this plate where we'll shine UV light and place it in the gel dock. And this will allow us to see our amplicon.
Yeah, we're gonna put in the screen what it's supposed to look like, but we're pretty much just exposing the agarose gel to UV light, so the ethyl bromide is gonna shine, and we're gonna see our amplicon in form of bands. So making sure you understand what is going on in that gel. So you're supposed to see two bands. So the top band, what is the top band?
So that is the Cree transgene that we're looking for.
So the mice that has the Cree transgene, we're gonna see that top band. The ones that doesn't have the Cree transgene, the primer wasn't able to bind, so they're not gonna show that band over there. So the mice doesn't has the Cree transgene. The bottom band, it's a control fragment. We haven't told you, but we use a second primer with a region that will amplify regardless of the mice having the Cree transgene or not. So if we don't see anything in the Cree band, at least we know that the PCR worked and we had DNA in our reaction.
So basically for this reaction, you expect to see at least one band, and that's the bottom control fragment. And if you see two bands, then you know that Cree recombinase was present in this mouse.
So using this, you use the PCR to confirm if the mice has the Cree transgene or not. And that should be it, right?
Yeah.
Thank you very much,
Yeah,
Andrea.
no problem.
So now you should know how to do a conventional PCR. Thank you.